Yeah.
Please.
All right. So yeah, first I want to thank Kadia for the very kind invitation and also for the opportunity to speak at the Zoom seminar. So somehow the pandemic is like a bad thing, but somehow actually it creates this opportunity for us to access like these different talks in a more convenient way, without like the restriction from the locations. So today I want to talk about the some work on the Tropiton tomography in space-time geometry. So this is based on a joint work with Gunther Ullmann and also Yang from Michigan State. All right, so first I just like a brief introduction of the usual Tropiton tomography and the work I've done so far. So the usual Tropiton tomography is motivated by this geophysical question of recovering the understructure of the Earth from the travels of seismic waves. And mathematically, one can consider like the Earth as some domain. For example, in R3, of course, we can also consider in like a more general way, like a manifold. So then with smooth boundary, so then the travel time is modeled by the distance between boundary points. So like on the right-hand side of the screen, so like the picture here. So the Z prime is the distance between the 2 points, Z and Z prime. And then the mathematically, this question, the travel time tomography, is called the boundary rigidity problem. And it asks the question like, given the distance function on all the pairs of boundary points, so can we determine the metric? So because the metric, it models, in the geophysics, the metric models the sound speed or index of refraction. And there is like a natural invariance for this question, which is if you take some diffeomorphism of the domain to the self and fixing the boundary, then one can check that the boundary distance of the pullback of this metric will be, by this diffeomorphism, will be the same as the original boundary distance function. So that means that this one can only hope like to determine the metric up to such diffeomorphism. And then the boundary rigidity problem in the Riemannian setting. So the earliest work of this question, mathematical question, probably is by Herglotz and Wickert and Zoipritz. So they consider the case if assume that you have like a standard ball and your metric is somehow radially symmetric. So it's and you want to recover this this metric. It's a scalar, one-dimensional scalar function. So you want to recover this metric, and they gave like an explicit inversion formula for that one. But more generally, if we consider like a more general some metric on a domain, then most studies so far is on a class of manifold. It's called the simple manifold. So by definition, it's a simply connected compact manifold with strictly convex boundary, and is free of conjugated points. And the simple examples are just like the usual Euclidean disk or the part of the hemisphere. So which is a bit less than the standard hemisphere, then there will be no conjugated points. So it will be a simple manifold. And then there's conjecture by Mitchell, which say the conjecture is that all the simple manifolds are boundary distance rigid. So if you are given like a compact manifold and the two simple metrics on this manifold, and they have the same boundary distance function, then the conjecture says that they should be equal up to such diffeomorphisms. And so for the conformal case, so if these two metrics, they are coming from the same conformal class, then this problem has been solved by Mokhomedov in 2D and by Mokhomedov with Romanov in higher dimension. And also for the case, if assume that either one of the metric or both metrics, they are conformal to each other. Not conformal, sorry. They are they're almost close to the Euclidean metric. Then there's a work also by Stepanov-Uma and Lasas, Shavdinov-Uma, and Burago and Ivanov. That's for almost a flat case. And for the general case, this problem has been solved in the 2D by Pestov and Ullman. And in higher dimensions, for the simple case, so far, the most general case problem is that we know that by Stepanov and Ullman, they showed that this is true for a generic simple metric. And in other on the other directions, if you assume in the 3D and higher, and assume that the manifold satisfies some convex foliation condition, there is a recent work by Stepanov, Uma, and Varsi who shows that for all such like metrics satisfied convex foliation condition, then actually the problem is also solvable. So this is mainly what we know so far for this boundary rigidity problem in the Riemannian setting. So then my talk is we want to somehow consider the similar the problem of the Tropiton tomography in the Lorentzian setting. So and the inverse problems in Lorentzian geometry has there are quite a lot of progress recently on this kind of topics. So two typical ones. One is the nonlinear hyperbolic equations on Lorentzian geometry, and in particular, this is due to the initial work by Krylev, Lasas, and Ullman for the nonlinear wave equations or nonlinear hyperbolic equations on Lorentzian manifold. And also there are quite a recent other works following their initial work. And here just like a very like a partial list. So I apologize if I missed any one on this. So, and also there are another topic on the Lorentzian geometry is light ray transform. So there are also quite a few like recent works on these topics. So, but today I want to talk about is another question, which is the travel time tomography on the Lorentzian geometry. So it's a nonlinear problem, and we just start with some setting for our problem. So first we consider in the whole the Euclidean space 1 plus m with some Lorentzian metric with signature -1, 1, 1, 1. So the time direction is -1 and the spatial direction is 1, is positive. And then given any like non-zero vector, so we call this vector is time-like if its inner product with itself under this metric is negative, and it's null or sometimes called light. It's light-like if it equals 0, and it's positive. It's space-like if its inner product is positive. And then you're given a smooth curve, then we see that this curve is time-like, null or space-like if the velocity vector along this curve is always time-like, null or space-like for all the time s. And it's called causal if its velocity vector is either time-like or null or null. It's for all the time t or for time s. So then, given such a Lorentzian space-time, then we see that it's time-orientable if we can find some global smooth time-like vector field on it. So given such a vector field, then it will give a orientation for this space-time, and so that a tangent vector is future pointing. Then if its inner product with this this global time-like vector field X is negative, and it's past pointing if this inner product is positive. So what I can use. Right, basically, the geometrical picture you show is like if you have at each point like the time console, you have its future. For example, the orientation is upward, then the vector is future pointing if it's like almost going upward, and its past point if it's going downward, the vector. So then, so given any two points in this space-time, so they represent like two events in the space-time. So then we use this notation much less than to mean that the y is somehow in the future of z, and there exists a time-like curve connecting z and from z and to y. And then we use this less than equal to sign to denote that if somehow we can find some causal curve from z to y. And then we use the notation the j plus of a point z to denote its causal future of z. So it contains all the points y who is in the causal future of this point z. So if like in the you show the Minkowski metric, then basically it contains like the future part of the time cone for this point. Okay, so that's some geometric setting for us. So then we want to define the measurement for our problem. So in the Riemannian case, the measurement is the distance function or the travel times between boundary points. And here, similarly, we have a version of the distance function for the Lorentzian case. So given a causal curve, and then we can define some functional on this family of causal curves by the following integral. So it's similar to like the usual definition of the length of some curve in the Riemannian case. Then if y is in the future of z, so if there is a future point in time like curve from z to y, then we call this this functional area of this gamma is called the prop time between these 2 points along the curve gamma. So physically, this quantity has the meaning called it's somehow the time recorded by a clock which moves along this curve gamma from z to y. So because we know that the recorded time is not only affected by these two events z and y, but it's also affected by the motion of the clock itself as an observer. So then we can define the so-called the Lorentzian distance, or sometimes called the time separation function, the tau g arbitrary 2 points in the following way. So if y is in the causal future of the point z, then we just take this tau to be the supremum of all these prop times of these causal curves from z to y. So otherwise, if y is not in the causal future, then we just assign this tau to be 0. So then, based on the meaning of this functional error, then basically the tau is somehow the largest prop time of all these curves from the point z the point z to the point y. And also from the definition itself, we see that we require that the y is somehow in the causal future of z. So this definition is not symmetric. And also, if this quantity, this Lorentzian distance is positive, then the maximum actually can be achieved by some under some prop conditions. Then this maximum can be achieved by some time-like geodesic from z to y in this case. So it's similar to like the Riemannian case. We know that somehow the distance, if on this compact manifold and under some conditions, then the distance should be achieved by a geodesic. So then we have this distance function. So then we, of course, the main question will now, if we are given this distance function on some with some like proper measurement, whether we can recover this Lorentzian metric. And but we will restrict it to like a smaller class, which is called the stationary Lorentz metric. So by definition, though, it can be written in the following way. So you have the pure time part, and also you have the pure spatial part, and you have the mixed part. So here the lambda is a positive function, and omega is a one form defined on this Rn. So one dimension lower than the whole space. And H is some Riemannian metric on this Rn. So with this stationary metric, then we know that it's easy to check that it's partial t. So the time vector will define the global orientation for this Lorentzian space-time. And for the stationary space-time, it actually provides some examples to the solution to the Einstein field equation. And one example is the Kerr metric, which models the vacuum space-time around some black hole. And there's a special case if this is like this mixed part, this omega is 0. So in that case, we only have the pure time part lambda and with the pure spatial part h. And in that case, the metric is called static. So it's a special case of the stationary metric. And one typical example is the Stewart-Strichard metric of the unrotational black hole. And in our work, we actually will also give some further restriction is that we consider this Lorentzian stationary metric, which is almost flat under some proper norms. I will define that in the coming slides. So one can consider that this almost flat stationary metric, you can consider that one as some like you get space structure for far away from some gravitational source. And also this almost flat stationary metric also appears in the linearization approach of solving the Einstein field equation. So you take the linearization around the standard Minkowski metric, then you will get something like this. All right, so with this, then we can define the corresponding the boundary measurement for our problem now. So of course, as the setting, we define the Lorentzian metric on the whole Rm plus 1. But of course, if we want to make some measurement, we want to restrict into some bounded domain so that we can make the measurement on the boundary of the domain. So then we let omega be some bounded domain in the Rm with strictly convex boundary with respect to the standard Euclidean metric. Then we assume that the stationary metric of our problem is it differs from the standard Minkowski metric only in this cylindrical domain by this R cross omega. So we have this in Rm the plane. So we have this omega. So then we have this this cylindrical domain. So in that we only assume that the metric G is it's different from the Minkowski metric inside this cylindrical domain. So outside that, then it's the same as the standard Minkowski metric. So then we will put all our interest just mainly in this cylindrical domain. So, but of course, this cylindrical domain is it's infinite, has infinite length. So in the time direction. So, but of course, it's not so reasonable just to make measurement on the like infinite time domain. So then we will restrict our measurement actually into some portion of the boundary of this cylindrical domain by letting this this gamma to be the closed interval from z to capital T times the boundary of omega. So this capital T is sufficiently large, so it depends on the metric and also depends on the domain omega. So So later, if we restrict it to like the almost flat matrix, then roughly speaking, this capital T is somehow it's close to like the diameter of this domain omega. So in that case, if for this T enough large, then we will have enough many time-like geodesics with whose endpoints are both on this portion of the boundary is omega. So then the measurement will be enough for us. So the inverse problem now is to determine the metric from this Lorentzian distance function restricted on this gamma cross gamma. So if the endpoints of this measurement is on this gamma we defined here. So, but even like we put quite a few restrictions, but still there is like a natural gauge similar to the Riemannian case, is that if you take some diffeomorphism from this domain to itself and also fixing the boundary, and then we can define a diffeomorphism in the space-time by letting it to be identity for the time variable. So we define this capital psi as the identity cross this little psi. Then one can check that the pullback of the metric by this capital psi. Then its Lorentzian distance function will be still be the same as the original Lorentzian function, original Lorentzian distance function for the metric G. So then the inverse problem now is it can be transferred to saying that if we know the Lorentzian distance function, whether we can recover this stationary metric up to such diffeomorphism. So here we need to recall that in the time variable this diffeomorphism is identity because we are restrict our consideration into just the category of stationary matrices. So if you take a diffeomorphism which also depends on the also have like changes in the time direction, then this might no longer give you a stationary metric. So then we could just restrict to this special type of diffeomorphism. So before giving the statement of our main results, so of course we need some geometric constraints to this matrix here. So one is that I already mentioned that we require that this metric to be almost flat. So it's close to the standard Minkowski metric in the sense of so here the CK0 it denotes the space of all the K differentiable tensors whose derivative on the boundary is 0 up to the order K. So we require that the distance between the stationary metric G with the standard Minkowski metric is less than epsilon for some small constant epsilon, sufficiently small, and also here the K is just some integer to be specified later. So generally this K will depend on the dimension of the space-time. So as the dimension goes larger, then this K also becomes large. And also there are some technical assumptions we need to impose in order to like solve this problem, use the method we have. So assumption one says that because remember that the stationary metric has the 3 parts. So it has a pure time part and the pure spatial part and also the mixed part. So we want to have some kind of compatible conditions for these metrics. So then assumption one says that we assume that there is some hyperplane outside this cylindrical domain, and we assume that for all the geodesics which is normal to this hyperplane, here the geodesic is a Riemannian geodesic with respect to this Riemannian metric H. So then we require that somehow this one form is orthogonal to all such normal geodesics to this hyperplane H. So well, we'll give a remark later why we impose this condition. So, and also the second condition is that given any two such like stationary metric, almost a flat stationary metric G1 and G2, and satisfy the condition 1 with respect to the thin hyperplane, we require that somehow the Riemannian distance for all the points x, y on the boundary of the domain, which is so that the vector from x pointing to y is almost normal to this hyperplane. So for all such pairs of points, we require that this distance of the Riemannian distance of these points for these two h1, h2 should to be the same. So if you draw this one in the picture somehow, so assume that if this is like somehow a projection onto this Rn of this space-time, and you have some hyperplane here, then basically the assumption 2 says that for all the x and y on the boundary, so that the somehow x minus y, because they are in the Euclidean space, so then this vector is almost normal to this hyperplane. So the angle between this vector, this is x and this is y. So the angle between this vector y minus x to this hyperplane is almost pi over 2 in that sense. Then for all such pairs of points, we require that the Riemannian distance of this between these 2 points matches between these two h1 and h2. So again, this is a technical assumption which is necessary for us to carry out the argument. So here is like 2 quick remarks why we impose this. So the assumption 1 somehow implies that we can find some global coordinates in this Rn, so that under this global coordinates, somehow the first component of this one form will disappear. So it only have the components on the x2 up to xn. So in particular, this gives us like a gauge for like gauge transfer of this omega, so that we can it will be helpful for us to carry out the argument. And the assumption 2 somehow it actually also appears before in the study of in the Riemannian case for the stability estimate by Wang. So, and also because for our problem here, we mainly we will restrict to the case if the spatial dimension is bigger than or equal to 2. So in that sense, actually this set of these points, pairs of points on the boundary, so that the difference, the vector between these 2 points determined by these 2 points is almost normal to the hyperplane. So this set actually is a very small subset of this boundary partial omega cross partial omega. So in terms of the measure of this set. And a final assumption is a priori estimate. So somehow we consider all these metrics G1, G2 is so that its H2 norm can be bounded, the difference of the 2 matrices, its H2 norm can be bounded by the H1 norm of the difference in a uniform way. So for some constant K here. So with all these assumptions, then we have the following theorem, which says that if you're given two almost flat stationary Lorentzian matrix, here the K the K index is which measures like what the almost flat means for the CK space. The index K is bigger than or equal to 2n plus 6. So then, as you see, like if you increase the dimension of n, then this index K will also become large. And here, our n is bigger than or equal to 2. And again, we assume that these 2 matrices, G1, G2, they differ from the standard Minkowski metric only on the cylindrical domain. And they satisfy the conditions 1, 2, 3. So under these conditions, then when we can show that there exists some constant T non, which depends on this domain omega and also this constant, this small constant epsilon. So that for any capital T bigger than this T now, then we define this gamma, which, as I said, it's partial of it's part of this boundary, cylindrical boundary. So this the closed interval 0 to T cross partial M. So then, if for this two matrix, the Lorentzian distance function matches on this gamma cross gamma, then we can conclude that there exists a diffeomorphism of this from this gamma to itself, so that for this capital gamma, which defined by this identity cross omega, so it's time invariant, so that under the pullback of this metric G1 by this diffeomorphism will exactly be the G2. So in other words, the G1, G2 is they are equal up to such like the standard diffeomorphism we mentioned before for the gauge of this problem. And if you want to write like in a component way, then basically if the G1 is the pullback of the G2, then this exactly means that for this function, the lambda 1 is just the pullback of the lambda 2 is the pullback of lambda 1, and this 1 from omega 2 is the pullback of omega 1, and H2, the Riemannian metric, is the pullback of the H1. So basically you can reduce all the things just into this one-dimensional lower space. So before go to some details of the proof, I want to mention that so our results can be regarded as a natural generalization of the early work in the Riemannian case by Stevanov and Ullmann. So now we show that this can be generalized into the Lorentzian spacetime under some proof conditions. And for the Lorentzian case of this travel time tomography problem, actually there are not so many works existing in the literature. So one early work is by Anderson, Dow, and Howard, so who showed that in the 2D case, and if you somehow, for their problem, also the measurement is different. So for our case, we somehow put the measurement is on some time-like boundary, because it's vertical. And for their case, they actually put the measurement is between two spatial-like boundary in the 2D case, and they show that the such kind of like some kind of rigidity property exists for if like I think for that statement to say that if a metric, a Lorentzian metric, a general Lorentzian metric has the same Lorentzian distance function as the Minkowski one, the flat one, then they actually have to be isometric to each other. So you can find such diffeomorphism. 2D, so we actually for our case we are at least in the 3D space-time because our M is bigger than or equal to 2. And also there's more recent work by Lassas, Oksana, and Yang, who studied in the real analytical category. So they showed that first that the locally the Lorentzian distance function can determine the boundary jet of the metric. So then from that, with the analyticity, then one can extend this determination to a global one. And for our case, we are working in the smooth category, and we are working in the 3D and higher. So it's different from the previous results. And also, if we consider the special case, if you let the metric just have this product structure, so it's negative dt squared plus some Riemannian metric H, then actually the Lorentz distance function can be, so in that case, if you take the projection of this time-like geodesics, then basically it will give you a geodesic with respect to this Riemannian metric H. So then these two problems, one is in the Lorentzian space-time and one in the Riemannian manifold. So they can be somehow transferred to each other. So in particular, the Lorentzian distance function also can be determined from, in this case, from the Riemannian, the length of Riemannian geodesics in this Rn. So in that case, somehow our results can be reduced, also can, as a corollary, so it also can determine the Riemannian case by some modification of the argument. So of course, then basically we get exactly the theorem proved before by first by Stepanov and Ullmann. So for two Riemannian matrices, which differs from each other, differs from the Euclidean metric only outside the, which differs from the Euclidean metric only inside some bounded domain omega. And again, they are close to the Euclidean metric in a prob CK norm. So then if the distance function of these two metrics are seen, then one can conclude that there exists some diffeomorphism so that the H2 is a pullback of H1. So in their paper, because in the arguments, they use some construction in the 3D. So their theorem is stated it is for 3D. But here actually, by combining with our results, then basically it shows that this actually is true in any dimension also. So then I want to still have about like over 10 minutes. So I can talk a little bit about the idea of a proof. So we mainly just follow the approach in the work by Stepanov and Ullmann in the Riemannian case. So for that, we somehow first is that from the distance function, then we can actually determine the so-called the scattering relation for this matrix. So in the Riemannian case, this is well known. So you're given this domain and then starting with some inward pointing vector on the boundary, this is ZV here. Then it induces a geodesic going through the manifold. So assume that the manifold is non-trapping. So then it will exit the manifold at another point and in the direction V prime here. Then this correspondence send this vector V to the V prime. It determines a so-called scattering relation for this metric. Then it is well known that for the simple manifolds, then the boundary distance function and the scattering relation, they are actually equivalent. So knowing one is equivalent to knowing the other one. And here our first somehow a lemma which say that this somehow is also, of course, it also holds in the Lorentzian case. And so we let this to define that. So we give some notation. So we let this capital G to be the flow of the geodesic flow associated with the Lorentzian metric. So written on the cotangent bundle. So it has two components: the position z and also the zeta, which is the velocity part. And with the initial condition, which is x non. So then basically this geodesic flow is a solution of some Hamiltonian system, where the Hamiltonian is just by the 1/2 of the inner product of this zeta to itself. And then also we have the corresponding Hamiltonian vector field. In this case, is a geodesic vector field, and just can be just defined in the usual way from the Hamiltonian theory. So under this notation, then so first we know that if we know this Lorentz distance function, the tau G1 and G2, they match on this gamma cross gamma, then we can conclude that the corresponding somehow the scattering relation for these two also will match. But here, of course, because the data is limited, we only restrict on this gamma cross gamma. So in this case, the scattering relation also it only holds for the only match for such vectors, the future pointing vectors, but so that the corresponding the geodesic, the axis position also should be on this gamma. So if you draw the picture, then our measurement is on this boundary of this cylindrical domain from 0 to t. So we only treat for these vectors so that it's the corresponding the time-like geodesic also acted on this gamma here. But if you somehow make it this vector more vertical, then it might eventually exit at some point away from outside this gamma. So of course the Tropiton information will not give us such kind of scattering relation. So we only know for this kind of geodesics. And also, since they have the same Lorentz distance function, so this also tells you that if you start with the same initial vector, then actually they will have the same exit time. So this is like a lemma which will be useful for us, especially. So it will be useful for us for later when we do some gauge transformation for the metric to simplify the expression of this metric. So under this assumptions 1, 2, as I said before, especially for the condition 1, so that this mixed part, this omega, will have like its first component will be 0 under some global coordinates. And with these assumptions and this lemma of the determination of the scattering relation, then actually we can simplify the expression of this matrix G1 and G2, so that roughly speaking, it's just like you do like you have this domain in the. So I think this is again a projection onto this one-dimensional lower Euclidean space, and originally you have some assume that, for example, this is the hyperplane by our assumption. Then assume that eventually you have something. So initially you have some geodesic which is normal to this hyperplane, and it goes through this domain. But of course, generally, if this is not Minkowski, then this curve will not be a straight line. So, but somehow the change of variables here, or its diffeomorphism exactly is we just like straighten this geodesic to make it into some curve, which is somehow is intuitive. It's like you make it to be a straight line. So under this change of coordinates, then you do it for both the G1 and G2. Then one can for this two under this change of coordinates, then actually we will still have this flatness condition, because this curve here, when I draw this picture, it looks like this blue curve is somehow quite away from this straight line, this red one. But actually, because the metric, by our assumption, the metric, so they are actually very close to each other. So it's more like a perturbation of this curve. So in that case, we still will preserve this closeness assumption. So the pullback metric, this G tilde, will still be close to the standard Minkowski metric. And more importantly, so in that case, under this diffeomorphism or this pullback, then actually this metric in the coordinates will have this special structure. So here the first component is corresponding to this lambda variable, and here the lower blocks corresponding to this metric H. And under this diffeomorphism, so it will have that in the first row and the first column of this H, except this corner one. So the rest parts, they all will be 0. And also then for the rest parts, these two, they are the mixing part for this omega. So again, as I said, because under our assumption, under this coordinates, then actually we can make the first component of this omega to be 0. So in that case, under this change of coordinates, we can make this metric to have the following special structure. And this will be useful for us to later when we do this to try to prove this determination results for the metric. So basically, if we can show that after doing this change of coordinates, then for matrix G1 and G2 looks like this special structure And we can show that if they have the same distance function, the Lorentz distance function, then it will imply these two matrices actually they are the same. Then this will give us the original statement. So basically, if we can show that the G tilde 1 equals G tilde 2 under this distance function assumption, then since the G tilde 1 is a pullback of G1 and the G tilde 2 is a pullback of G2, so this will automatically give us that the G2 will be a pullback of G1. Yeah, and also under this change of this diffeomorphism, so it actually will preserve the distance in that case. And the main part is or the main ingredient is just integral identity from the early work by Stepanov and Ullmann. So this integral identity actually the proof is quite simple, but actually it's very useful. And also it has been applied to many different questions recently. And one probably most important application is in a recent work by Stepanov, Ullmann, and Varsi for solving the boundary rigidity question in the under the assumption that with the convexity foliation assumption. So one can also reduce that one into the integral identity question and to invert that one. So here the integral identity basically says that the difference of the scattering relations for these two matrices can be expressed in terms of some integral along some time-like geodesics in our case, because we are considering the boundary distance function is with respect to this time-like geodesics. And the right-hand side exactly is some X-ray transfer along time-like geodesics. So as I mentioned before, that most of this X-ray transfer question so far for the Lorentzian setting is mainly for the light ray transfer. So here we need to treat this X-ray transfer along some light time-like geodesics. And here the blue one, you can treat this one as a weight for this ray transfer. So under this almost flat setting, then it has the following expression. So it's the matrix, you have a matrix here, and with some perturbation depends on this epsilon, this constant. And this red one part, it carries the difference of these two matrices, the G1 and G2. So it carries both the distance and also the gradient of the distance. Because our matrices, they are stationary, so this gradient actually is only with respect to this spatial variable. So then we can take use of this integral identity and actually only take part of that. So if you take the lower part of this weight and with this gradient, the second part of this gradient, then this will give us the following identity under our assumption that because our boundary distance function is the same. So by the lemma, then they determine the same scattering relation. So we will have that in this integral identity, the left-hand side, this one will be 0 in this case, if the Lorentzian distance function matches for these two matrices. Then we derive the following integral identity. And so basically now the question is to invert this integral to determine this difference, this m. And the way is it's similar to the Riemannian case, is that we apply the Fourier transform in some sense to this to this integral, and then move the part with the epsilon, the small part to one side. Then basically the main part on the left hand side will just be the Fourier transform of the gradient of some matrix function. So, and here the Fourier transform is with respect to this spatial variable, because our metric is stationary. So if you consider more generally, if the metric also depends on the time variable, then you also need to take the Fourier transform of the time direction if you want to somehow fully determine that. But we know that if the metric is time dependent, then actually there will be issue because as this, it's similar in the light ray transform is that one cannot recover all the singularities from the light ray transform. So basically, you can only recover this space-like one, but not this time-like one. So in that case, if the metric actually depends on the time, there might be some issues. So I will mention that later, maybe at the end of the talk, a little bit. So then after taking the Fourier transform, we get this. Then because our there's another issue is that because our metric it mix all this like the pure time part and the pure spatial part and also this mixed part. So if we want to uniquely determine that, we need to separate these contributions from this different part of the metric. And then thanks to this time-like geodesics, actually, because we can tilt this, by our measurement, we can tilt this direction of this geodesic a little bit. It's still in our measurement set. So in that sense, we can actually, we can separate these contributions from this different part of this, from this function lambda and from this one from omega and also from this remaining metric h. So we can separate their information to uniquely determine that. And yeah, eventually just by, since we know that the metric is close to the Minkowski, so by a perturbation argument, one can show that the gradient of this m actually is 0. So then since m is compactly supported inside this domain omega, so this actually implies that this m actually is 0 itself. So that solves the invertibility of this X-ray transform question and also the original travel time tomography question. Right, just like a final remarks. So as I said, there are only very few results existing in the literature. So our work just can be just like some early attempts to study the Tropiton tomography problem, which is a version of the usual problem in the space-time geometry. So and also for our case, here we only consider the metric is almost flat and also with some assumptions. But here, of course, there are quite a lot of work can be done in further for this problem. One is to just reduce this geometric constraints we impose here. So all these assumptions 1, 2, 3 somehow is some technical assumptions which is necessary for carrying out this argument. So if one can like go around that, use another argument for the proof, then probably one can also reduce some of these geometrical constraints. And another one is that so metric is close to the Minkowski one. So of course, it's interesting to see like how things are going if the metric is far away from this Minkowski matrix. So that in the general setting, and of course the more general one is if you also consider this non-stationary Lorentzian matrix, and for that case, as I said, if the metric also depends on the time direction, then one might need to impose some other type of assumptions because from the information we know that it cannot recover all the singularities from the macrolocal point of view. So in that case, one need to it might be necessary to impose additional assumptions so that one can treat the non-stationary case. So yeah, so I think that's all my talk. So thank you for your attendance.
Thank you very much, Hanming, for the very interesting talk. Thank you very much. Are there any questions or comments, please? Any questions or comments, please? Please feel free to unmute yourself.
Hi, Hanming, this is Teemu. Thank you very much for this great talk. So could you please explain me a bit what's the connection of that tau function and this L function, which was the exit time of your geodesics, how they are connected, because I think in the Riemannian case they are the same, but I guess now they are different.
Right. It depends on the parameterization of this time-like geodesics, because this tau it's achieved by this time-like geodesics, and for the time-like geodesics also it has like constant speed. So then this tau, this L basically is like it equals this tau up to a scaling.
I see. Thank you.
Thank you very much, Teemu. Thank you very much, Hanming. Are there any other questions or comments, please?
The illustration at the beginning of your talk was the Earth with its various layers underneath. And in fact, I think that's an illustration for the whole seminar. There's another sort of related question that might be relevant here. I mean, suppose instead of a unknown metric inside that, you have surfaces where there are jumps with more or less constant metrics in between. I mean, this is what I think the geophysicists would really like. How could you find those surfaces by this sort of method? Is that a clear question? So the diffeomorphism the diffeomorphism invariance plays a role still, but I don't think it's quite the same.
I'm not sure for that case. So you mean like in this case, the metric has some jump along some surface?
Yeah. Could you find those surfaces?
But then the scattering relation will be 1 to many, right? It will split.
Yeah, afraid so.
Right.
Yeah.
Right.
We have papers on that, but use the wave equation or the elastic equation. In other words, the model is the hyperbolic equation. And still, most of the information comes, actually all information comes from singularities, but we do not restrict it to dynamical information.
Okay.
And also the other works, I mean, in this direction, de Hoop and his collaborators also have this for the acoustic equation and so on.
Lovely.
Thank you very much for the great discussion. Are there any other questions or comments, please?
So yes, I would like to ask a question. Thanks a lot for the interesting talk, Hanming. So is my understanding correct that you basically first reduce to the scattering relation and then you sort of forget the time separation completely, and basically the argument is about the scattering relation?
Right. So once you can determine the scattering relation from the boundary, the Lorentz distance function, then you just use that. Of course, you still need to use the distance function, because you want somehow the travel times of these two geodesics with respect to these two metrics, they are the same. So this is the integral. Eventually, they have this geodesic will have the same exit time for these two metrics.
Right. I see. Okay.
Of course, from that integral identity, then it mainly just like it can be treated as like a transfer from the distance function to the scattering relation, because the one side of this integral identity exactly is the difference of the scattering relations.
Right. So what I'm sort of getting at is that if you look at these scattering relations, then it makes sense to restrict these to the null geodesics, right? To the case that X here is null vector, right? Whereas for the time separations, if you restrict this only to the null vectors, it doesn't give you anything, right?
Right.
So So I was wondering if maybe these techniques could be used in this case where you are restricting only to null vectors and start from the scattering relation. And is there any hope of using something similar as your
there
argument
would be some issue is because in the argument we also need to split, as I said, the contribution from this different part of this metric. So in that case, if you only have this null geodesics, then there might be an issue to split the information from this function lambda and from the Riemannian metric h, because one is 0 degree and one is 2 degrees. So they are both even degree and the information will mixed together. So here the time-lag geodesic exactly can help us to separate these two informations.
Right. But you would still expect to be able to separate the first order part from or sort of separate even and odd orders, right?
Right. But yeah, so using the null geodesics, you should be able to separate the even and odd part. Yeah.
Right. And is this the only place that sort of goes wrong in the argument? So I think it would be still quite interesting. Let's say that you, for some reason, know already lambda, for instance. You could maybe then recover omega and h.
Then I think this, if you are given this scattering relation, then this argument somehow should work in that case if you're given scattering relation for the light rays. Yeah.
Okay. Yeah. Thanks a lot once again.
Thank you.
Thank you very much. Are there any other questions or comments, please? Okay, if not, thank you very much, Hanming, for the very nice talk. Thank you very much, everyone, for coming. Thank you very much.